All right? So this axis of least inertia, this solution where we minimize the distance to the axes, the sum of the square distances, which is the same as maximizing the distance along, says it has something to do with this matrix B transpose B, where B was that list of all those points. Here's another algebraic way of thinking about this, okay? Using our old definition of B transpose B, okay, you'll notice that what it is actually this matrix. Okay, sum of x squared, sum of xy's, sum of xy's, sum of y squareds. Well, that's just the covariance matrix of the points, assuming that they're about the origin. Okay, so I don't have to subtract out the mean. That would be the covariance. Speaking of which, yet one more way of thinking about this is that B transpose B here is the sum of this XX transpose. That's what's referred to as the outer product. And if it's about the origin, I don't have to subtract off the mean, but here it is written just like that. That, again, is the definition of the covariance matrix. This makes some sense for those who are thinking about it. The covariance matrix is a relationship between the expected value of the squares, the sum of the squares of points distributed about the mean. So that's actually, if you think about it, the thing that we wanted to know. We want to know the greatest variance. For those of you that care or you're thinking about it, if you think about a covariance matrix as an ellipsoid in space, your eigenvectors are going to end up being the major axes of these ellipsoids. Here's a quick question for you. How many eigenvectors are there? Not on the planet, in general. Okay, well, normally for a real symmetric, and by the way, these things are typically symmetric because if you take a look here, right, I've got the sum of the squares, but on the off-diagonal terms, I've got the same values, the sum of the cross terms, right? So if I have a real symmetric matrix, in general, if it's size n by n, I normally would have n real eigenvectors and distinct eigenvectors. There are some degeneracies if you have identical eigenvalues and then you have ambiguity. We're not going to worry about that too much. But just remember that normally, and the reason I say normally is later it's going to be a little different, normally with an n by n matrix, I'm going to have n eigenvectors. So graphically, we can look at that like this. So here I have a beautiful set of points. Aren't those delightful? Distributed in 2 dimensions. And which way do you think is the principal eigenvector? Well, probably something along like that, right? That's going to be the axis of least inertia, right? Or of greatest variance. Get used to this idea that it's greatest variance. And in fact, that's what this nice little picture shows us. And this is showing us lambda 1, meaning the first eigenvalue, large eigenvalue. And what direction is the next eigenvector? Well, as you know, it's perpendicular to that, right? Because eigenvectors are perpendicular to each other, and the next one is the next most variance, etc. With 2 dimensions, it's hard to show. There's only 2 here. Why am I telling you all this? Let's talk about dimensionality reduction. So here I've got a bunch of points, okay? And these points are in 2D, all right? It's called kind of green and red, but that's sort of a joke. We're not going to worry too much about why it was done that. What you should notice is that in the middle here are these orangish yellowish points. Do you see why it's orangey? Red plus green makes sort of yellowish. So along that diagonal, they'd be kind of yellow. I don't know who did this originally, but it's kind of cool. All right, if you think about these orange points, let's think about how they're distributed, okay? So they have a mean somewhere, and they've got a set of eigenvectors, right? They've got a covariance matrix that describes them. They have a axis of least inertia and then the next axis. So here you're seeing the points, the orange points are x. X bar here is supposed to be their mean. And then we've got the big eigenvector v1 and then the smaller one v2. And the idea is we can represent those orange points by only their v1 coordinates plus the mean. And what that would mean is, essentially that we're going to think of all the orange points as just being on that line. And all I'm going to tell you is where on the line they are. And we're going to essentially ignore the amount that they're off that line. So we've just reduced the dimensions from how many? 2 to how many? 1. Okay, that doesn't sound like that big a deal, nor is it. But in higher dimensions, this could be a huge deal. Imagine you've got something in 10,000 dimensional space. And yes, in just a minute, we're going to do a 10,000 dimensional space. If you said, well, I'm going to represent them by 1 number, or even 30, that would be a huge reduction. So if I said, well, what direction does it vary the most in, and I just give you that value, if that's good enough for what we want to do, you've reduced the description from being a lot of numbers to being a much smaller number. In fact, we can sort of express that here algebraically in terms of just thinking about it, whatever dimension x happens to be in. So if I've got a whole bunch of data points in some n-dimensional space, what I want to know is the direction of projection, and let's say it's v, all right, that if I projected those points after subtracting out the mean, that I'd have the greatest amount, right, the greatest variation. And that's what that says here, right? So take x, subtract out the mean, dotted with the v, summed over all the x's, take the norm, take the square. Well, that can be written as an expression like this of just v transpose AV, where A is just this outer product. Okay, that's the covariance matrix that we're familiar with before. And as we said before, the eigenvector with the largest eigenvalue lambda is going to be the one that captures that greatest variation. In a minute, I'll give you a little argument about why it's the eigenvector with the largest eigenvalue, or you can just take my word for it. And in fact, the smallest eigenvalue would be the least amount of dimension. So basically, what we're going to have to do at some point is take the eigenvectors of this covariance matrix.
What if your data distribution looked like this? Can you guess the two largest principal components or eigenvectors? Let me give you some options. Do you think this could be one? How about this? Or these two? Remember, you want to pick the first and second principal component. Type 1 for lambda 1 and 2 for lambda 2. Leave the remaining two boxes blank. So, did you fall into the trap? Let's look at the distribution again without the clutter. If you were to approximate this with an ellipse, what would it look like? Well, something like that. Which is the major axis here? That's right, horizontal. And that would be the first principal component. As odd as it may look, the second principal component would be orthogonal or perpendicular to this. So, this is 1 and this is 2. Intuitively, this doesn't look right, does it? But it's exactly what you told PCA to find. The axis with the most variance would be the first component, and the one orthogonal to it would be the second. PCA is good for characterizing a single class of instances. It can reduce the effective number of dimensions needed significantly. But what if your data came from two classes or sources? If you wanted to characterize two or more classes at the same time, PCA might not be a good choice. This is especially true if the axis of most variance for the source distributions are not perpendicular. There are some other approaches for characterizing multiple non-orthogonal classes, such as ICA or independent component analysis. One big difference here is that ICA does not require the components or basis vectors to be orthogonal. Anyways, this is probably going off track from the current discussion. Let's focus back on PCA and see how we can apply it to images.
What does this have to do with images? Well, let me tell you. I'm going to introduce this using the notion of face images, because frankly it was this eigenvector approach to doing face recognition that really, I think, caught people's attention. Think of an image now not as a two-dimensional thing, but as just one great big long vector, okay? So it's just got a whole bunch of values in it. So for example, suppose I had a vector that was 100 by 100 long. How many pixels is that, Megan? 100 by 100.
10,000.
10,000, you got it right. 100 times 100 is 10,000. So that's just a 10,000 long vector. If I don't worry about the fact that there are pixels located in a particular position, which by the way is going to be an interesting problem later, if I just think of them as values, that's a 10,000 dimensional space. Right? There's 10,000 dimensions. Each dimension has a value. What's the value? It's the value of the pixel that corresponds to that location. This location is another pixel. Its value 18, fine. That's its value here. So the idea is that an image is just a 10,000 dimensional vector. Question. How many of those 10,000 dimensional vectors, how many 100 by 100 pictures, are actually pictures of faces? I mean, just of a face. Answer, not a whole lot, okay? In fact, most values, right, if I just randomly put numbers in that vector, right, I get out, random pixels everywhere, right? The idea is that faces are a very special set of vectors. They're not all possible vectors, and they're not distributed everywhere in this image space. They are on some particular, what's referred to as a subspace, sometimes a manifold. Okay, they're in a subspace of all images. Okay. By the way, we sometimes call that subspace face space. What's face space? It's the subspace in the space of images that are the pictures of faces. All right. So here's what we want to do. And this is color-coded, so we want to build a low-dimensional, because we're going to try to get a nice dimensionality reduction going on here, linear, we'll talk about the use of linearity to be able to just do dot products to get our coefficient, subspace, so it's going to be some reduced space, that explains most of the variations seen in face images. And that's just drawn out here. This looks just like what we had before, where we had blue dots and orange dots. Now I'm telling you, well, actually, even though this is drawn as just a two-dimensional space, because I can only draw two, it's a 10,000 dimensional space. 10,000 pixels. You're like, okay, fine. 10,000 pixels. And the idea is, let me find the direction or directions in that image along which most of the face images lie. And that's what it shows here, that this cyan color is sort of ideas that the face images are there. And then we've got all these other images that are not images of faces. They're cats. Well, they're all sorts of things, okay, whatever the internet has pictures of, and all other possible things, all right? So how are we going to do this? Well, it's not going to surprise you. We're going to use principal component analysis, because when you see a picture that looks like this, where I want the extended dimension, I want to use that extended variance. So here's how we're going to do principal component analysis for this. Assume we have m data points, okay, so x1 through xm, all right, where they're in some d-dimensional space, order the d, where d is big, really big, at least 10,000. Maybe it's a million, okay? So if I had a 1K by 1K image, that would be 1,000,000 pixels, right? So I'd have a 1,000,000 dimensional space. So what we want is some direction in that big space that captures most of the variation, okay? And furthermore, and this is sort of important, not sort of important, this is really important. If I talk about a direction, and let's suppose u is my direction, how would I find out where it lies along that? Well, what's nice about this is, because we're doing everything linearly, we're just going to take the dot product of x minus its mean. Why are we subtracting the mean? Because none of this stuff works if you don't subtract the mean. Remember, we're doing variation about the mean. So we subtract the mean and we take the dot product. And then u of xi, that would be the coefficient. So we want to find the u that captures most of the variance. All right? Well, you know already how to do this because we've been talking about it, right? So here's the same expression that we had before, but I've sort of used the notation we just developed, right? We're going to say the variance along u. Well, we want it over all the possible points. So what we say is, okay, well, we're just going to take that average. Here is x minus mu dotted with u. We multiply it also by its transpose so that we get the square value. Okay, so that's just the same thing that we had from the previous slide. I'm just going to rearrange that a little bit, right? So I can pull the u's out here and another u out there because it's transpose, transpose. And what I have left here in the middle, well, what is that? Right? That's just the covariance matrix, and we'll call it the covariance matrix sigma. And we've talked about how for finding this, the axis of maximum variance, we need that covariance matrix. But think about this just a little bit more. So that variance of u is u transpose sigma u, all right? All right, now follow me carefully, all right? U is some vector. Which vector? U, not me, u. A matrix times a vector, since everything is linear, if I describe u as being made up of a bunch of components that add up to u, it's the same thing as sigma times those bunch of those components. So in particular, the components could be the eigenvectors of sigma. So I could express u, the eigenvectors of sigma point whatever direction they point. I can think of u as being made up of a sum of those. All right? So u is a unit vector. Okay? It can be expressed in terms, that's what it says, the linear sum of those eigenvectors of sigma. The question is, which of those directions would return me the largest value? Okay? Well, we know that